Hello everyone and welcome to today's webinar. We're going to talk about how you can minimize earthworks costs for your road project. Okay, so with Softree Optimal, there are mainly two major benefits. First, adding earthwork optimization allows you to deliver the lowest cost design by mathematically reducing your subgrade construction costs. And second, it also allows you to design faster, whether that's through testing feasibility for your design constraints, having your profile automatically generated, or exploring alternative horizontal alignments. There's lots of ways to help you design faster and smarter. In this introductory webinar, we're focused on demonstrating how earthwork optimization works and achieve these two benefits. So for today's agenda, we're going to focus on demonstrating how to optimize earthworks, including movement and embankment excavation costs for a road project. We're going to specifically cover different types of projects suitable for earthwork optimization. Truth be told, it's important to understand that not all projects benefit from this technology. Next, we'll be showing how to input constraints and test feasibility options, working with subhorizons and different ground types, as well as how to update your costing model. And finally, we'll tackle interpreting results. And with that, I'll now pass over to our resident training manager, Matt.
All right, thanks for the introduction, Andy. So today we're going to focus on our vertical optimizer. For that, we'll need some kind of topo surface for our ground survey. Your traditional design, everyone here has probably done a traditional design where you'll go through and figure out the alignment that you want to go with. Our optimizer kind of takes that traditional approach and turns it into a semi-automated one. So it's going to leverage mixed integer linear programming in order to generate a vertical alignment for us. Oftentimes, the difference between the optimized alignment and the traditional alignment can be fairly subtle. If you're standing and looking at a cross section, you may not pick out that in the grand scheme of things, it makes a big difference. But if you're up or down a foot spread over a long distance can equate to a lot of volume, which equates to a lot of earthworks. So yeah, here we're just kind of highlighting the difference between the two alignments. So how does it work? As I said previous, we need an existing ground. So LiDAR is a great survey option for that. You get a large area and high quality data. For our optimization, we're going to need a preliminary horizontal alignment. So we don't necessarily need a vertical alignment to start optimization, but we do need to know where the horizontal is. And if we use our horizontal optimizer, which I'm not going to talk about or focus on today, but that will take your preliminary horizontal alignment and adjust it to find a better route. We also need to assign the cross-section geometry for our road. And we'll need to make sure our costing model is reasonable. And then we'll input any constraints that we have. So for costs, we can add a bunch of different costs. We can set up costs for your cut, fill, and we can vary those costs by material type. We can also assign costs for your surfacing materials. We can include the cost for your material movement and loading that material. And we can include other costs such as costs for culverts, clearing and grubbing. Those costs by default aren't or the culvert cost by default isn't included in the optimization. We also have pit opening costs. That is included in the optimization if you want to add that in. For constraints, we can include a bunch of different constraints. So we can add in your maximum grades, your minimum K values, can assign control points. So our software is going to look to optimize your alignment based off of the Earthworks. So it's not going to design things like your bridge abutments or something like that. So if you know exactly where you want those bridge abutments are, well, maybe that's a good spot to assign a control point to make sure you meet that location. Then we can assign other geometry constraints, like if we need to be in full bench for a given area, and we can control material. So biggest thing for whether a project's suitable or not is, can you move the vertical alignment up and down to minimize your costs? If your vertical alignment is fixed, you're not going to be able to move the alignment up and down. So there's no savings there for you. And also if it's really constrained, it may be that there's not a lot of wiggle room to improve your costs. So with that, we'll jump out of the PowerPoint and jump into a few projects. So my plan today is to kind of go over a few different examples, touch on different characteristics, some behavior you might bump into, and focus on how we can control what's going on. So first example, I'm going to start out with a project that's been done in another software. I think it's a reasonably well done design. And my surface, I'll use LandXML for it. And then the alignment, I'll use a LandXML for that. And we'll see if we can do better than the traditional design here. And then I'm also going to purposely make an imperfect solution, and we'll show how we can accommodate that. So I'll save that. And for my alignment, it already exists in this case, so I'll bring it in as a LandXML. Now, most of the time, if I was doing this, I would just jump in from scratch and click an alignment in from scratch to show the full behavior. We'll just do something a little different for the sake of variety. So here we are. I'm going to just change my background to something else just so we can see what's going on. So we've got a road alignment project. Let's see our traditional design for our vertical. And our cross-section geometry, in this case, I've got our default cross-section geometry assigned, and it's appropriate for this example. So I'm just going to leave that as is. So that's that. The costs are going to play a big part in how things behave. So our costs are carried in the ground type information. Now in this case, I've just got one material type assigned. I'll work with a different example with multiple materials here later, but one material type assigned, and the costing information is carried over here. So for this, I've got overburden. I'm telling it that it's going to cost $12 a cubic meter to excavate, $4 a cubic meter to place and compact. And for my hauling, I've got free haul, overhaul, end haul, all separated out, and I've got different unit rates for those. So hauling, free haul material, $8 cubic meter kilometer, no loading cost. Whereas if we go down to end haul, we've got $2 a cubic meter kilometer, but it's going to cost me $2.60 a cubic meter to load. So that cost dynamic is going to drive what the software is minimizing. And we can change our handling costs by material type. So we've got hard pan, we've got solid rock, and solid rock's going to cost a lot more. Now, all these numbers are user definable, so you can put in whatever works for your project. And if you're using the software just for optimization of your alignment, these don't have to be bang on. The relationship's going to remain true. So if we minimize our cuts and fills and minimize our material movement, we're going to get a cheaper solution than if we have lots of cuts and fills and long hauls. So with that, let's come over here. We'll see what we're at to start. So I'll just do a quick recost. So using that costing functionality that's already in there, we can see what the traditional design is going to cost us. And right now, this is just showing me my subgrade cost. And in one of our following examples, I'll show how to include your surfacing material. So this is saying it's going to cost $854,000 to build as designed. So I'm going to do a new optimization. I'm going to tell the software to sample along the length of our road in 20-meter intervals. I'm going to tell it to use variable curves and tangents. So in this case, I'm using variable curves and tangents so I don't have a bunch of curves butted right up against each other. If this was a low volume road that I wanted to just be as cheap as possible, I'd probably go with curves fast, in which case we don't need those tangents between our curves. I'm going to tell the software that I want my minimum curve and tangent length to be 60. And let's assign our minimum K values. And we'll hit add edit to update this list so that change takes place. Control points. So I mentioned oftentimes you'll pin down an elevation for your bridge abutments if you have bridge abutments in your project. Most common location to use your control points is at the start of your alignment. So obviously you don't want to start your upgrade or new road in a big cut or fill, not be able to drive onto it. So yeah, we're going to account for that here. And since we're doing a realignment, we're going to nail it down at the end of the alignment as well. Pits, won't worry about that. We'll talk about that in another example, but if we expected a surplus or deficit of material, we could account for that. Unit costs, we've already accounted for. And constraints, we'll talk about that in another example, but we can add a bunch of different constraints to account for the constructability and geotechnical conditions that you may have for your alignment. So with that, it's kind of a really basic setup. We'll do our optimization. This is going to take probably a couple minutes to do the sampling. And just while that thinks, I'll come back and just talk a little bit about costs. So the costs we have in there are pretty reasonable, at least the relationship is. We've got our solid rock ground type is going to cost a lot more than overburden. But they are user-defined values. So many of you probably have a good handle on what values to put in there. If you don't, sometimes depending on your jurisdiction, you may be able to just look up where you're working and they'll give an average cost for different items broken down, and you can just pull those numbers right into your model. Other alternatives, you may be able to just contact a local contractor. If they're bidding on jobs based off of volume and material movement, there's a good chance they know those what they'd charge offhand. And if you're looking for a more universal solution or being able to derive those costs yourself, you may be able to look up rental rates for equipment in your area and combine that with cycle times to come up with your own per cubic meter or per cubic yard costs. And if you're looking for cycle time information, I'm a big fan of the CAT Performance Handbook. And let's see here. So this one has lots and lots of pages, and we can, we'll just see here, 575. So each different piece of equipment has a different section on it. But yeah, cycle time and estimates, and it'll give you maximum values and then different factors to equate it to real world conditions. Now back here, back into the software, our optimization is solved. Our cost went down from 854 to 797. So just looking at this, our mass haul balances are very close to balancing. But just at a glance, I'd look at this and say, well, I'm not really happy with that big fill slope. And that's fine. We can adjust it by hand. So we can come in here. We're not stuck with whatever alignment we generate. We can move it by hand, or we could say, okay, I want to shift down shift down 2.2 meters. So our current elevation is, whatever it is, 352. And we could come in here and we could add another control point. So that we want to pin down at a certain location. So at station 190, we want the elevation to be 350.6. There we are. And we can re-optimize and away we go. Now, rather than watching that do its thing, we'll circle back on this after and we'll go look at another example where we're dealing with a little bit more construction restrictions. So in this example, we've got our traditional design. It's giving us a cost of $182,000 to build. We're going across a swamp here and a swamp here. Well, maybe we can optimize that. So let's look at what we can do with our constraints. So in here, this is set up largely the same way as I did the last one. Different design parameters, just different class of road. Control points, I have my start alignment nailed down. Pits, I'm going to add in a pit later, but first let's just go to constraints. And for those swamp sections, let's tell the software I want to be in a meter of fill from station 80 to 170, and then a meter of fill from 630 to 720. I'm going to run this and it should give me some kind of funny results just because it's going to try and balance our alignment internally. And it doesn't make sense to do that in this case, but we have the controls to make it smart. So again, going through, doing its sampling, and then we'll look at what it gives us. And so just jumping back rather than staring at a computer thinking, this one that we were previously doing, where we've changed our control point. There, we've fixed that and it didn't cost us a whole lot to do it. So yeah, pretty smart. It's pretty dynamic. You don't have to re-optimize it either. I could have just changed that, recalculated if it was a negligible amount. Back to this other one. We've got our design, but it's kicked out a funny result. So here we're forcing it to be overlanding. It needs to address that deficit of material that we've created. So it is pushing a through cut to generate enough material to deal with on that end. Now this other swamp that we're crossing, it looks like it came out pretty reasonable. Probably don't have to change any settings there. Nice straight push to generate our material. Can make sense. But back here, if we want to control that and not have a funny approach, we absolutely can. So we can go back in this. I'm going to want to do two things. So I want to add a pit at the start of our alignment. So we'll make it a borrow source. And in this case, we don't have an actual pit location right at the start of a road. So if we want to account for the dead haul distance to get from our start of a road to the pit, we can. So click add, borrow, and I'll say it's 2 kilometers away. Now another thing with your pit excavations, oftentimes it'll be cheaper to do that primary excavation, just everything is set up for production. So I'm going to change my excavation cost to $6 a cubic meter rather than the ground type value I have set at 12. So that's fine and dandy. Now, even if it's cheaper to generate our material from this location, it's pretty wet ground. We probably don't have access over that swamp. So we're going to want to control the movement direction. So we'll come into our constraints tab and we're going to tell it that it can only do forward movement from station, let's do station 90 to 170. So forward movement. And we'll hit OK, and this time we'll re-optimize. Now, with this, It may not be a cheaper solution than the previous optimized solution just because it's more constrained, but we've also let it generate material at $6 a cubic meter. So we'll get a better alignment out of it by accounting for the those real world constraints that you have to consider when you're building. So it's going to cost a little bit more than that previous example that we have, but it's going to be buildable in there. And that makes sense too. We're generating our material at the start of our road from a pit. So we've dealt with the deficit, and then afterwards it makes sense to follow the ground as closely as possible to minimize the earthworks. So that's kind of one matter of you ran it once and it didn't look like it made sense. Well, we can evaluate what's happening there. It makes sense that that's happening, and add in the information that we need to get a better solution. And this next example I have, I'm not going to actually optimize. It's already been optimized, but we'll talk about dealing with multiple materials. So in this example, I've gone to assign by range, and I've told the software that along the length of my road, I've got multiple materials at different depths. So from station 0 to 931, I've got hard pan over fractured rock over solid rock. Now, these materials have their own geotechnical parameters associated with them, different cut and fill factors as well to account for shrinkage and expansion. And then each one has its own costing parameters associated with it as well. And then we've got our quality factor as well. So here, my gravel is a better material than overburden. That's not as good as gravel, but it's better than overburden. So Q1 to 4. So we've got those materials assigned along the length of a road at different depths. We can see our horizons here. If we're going through a cut, we can also see that it's pulling in those geotechnical parameters for cut and fill slope values. So that's that. Now, ground types make sense then. So what about surfacing? If I want to account for my surfacing, I can come up here and I can tell the software that my surfacing layer 1 has to be Q3. Surfacing layer 2 would be my well-graded base. And then when I assign my pits for this one, I've told it, okay, at 1141, I've got gravel. At 1375 is going to be where I'm manufacturing my well-graded base. Now, with a conventional mass haul diagram, you're losing out on the complexity of your material movement, and you're losing out on the fact that we can account for each individual material and where it's required to go with the optimization. Now, the way the solver is evaluating that is not off the mass haul diagram. It is off the OptiHaul diagram. And here we can see that it's accounting for material moving in different directions. And if we hover over this, it's going to tell us what each material type that we have at a given location, which direction it's going and how much is there. So a lot more detailed, and we can copy that to the clipboard and paste it into Excel, and you get a really detailed tabular breakdown of that information. And then the last thing I wanted to show is kind of contrary to what I introduced as you need the ability to move your alignment for it to be useful. That is true if you're looking to optimize. Oftentimes folks doing overlays and widening jobs will still want to show vertical curves and have an idea whether they're adhering to their design parameters for their said road. So we could use the optimizer kind of in a funny workaround way. Rather than using the cross-section geometry that I'd like, I've got one temporary cross-section set up that's just going to give me the same geometry whether I'm in cut or fill, or same volume whether I'm in cut or fill relative to what's going on. I'm going to assign that to my length of road. And so since the optimizer is going to look to minimize our earthworks, it's going to want to keep this as close to the center line as possible. Now I've got this set up, it's doing its sampling. I've got a really narrow vertical band for where it can put the road. It has to be within a meter, or sorry, a foot in this case, of ground. And I've got the standards to match my minimum K value for my project. So we'll hit process. I'm not going to run this to optimal either. I'll let it find a viable solution, and then I'll hit cancel, and we'll see get more or less align a best fit, and then we can put our actual road geometry we want back onto the alignment. Yeah, I don't need to run this to the end. I'll let it run a little. That's probably long enough. So now I've got my curves assigned. They're matching the ground that's underneath it. If there was any locations where my minimum K couldn't be adhered to, I'd see big spikes in my mass haul, not plus or minus a quarter of a cubic yard, and then we could identify if we want to realign those or just change the design parameters. Yeah, and we can just switch it back to our widening, and away we go. So yeah, that's the information I was hoping to cover today, and we'll open it up to questions. And we've got a question: can I change the currency in the costing? Absolutely. So in here, I guess first of all, if it's a matter of what values you're using, you can change the ground types to suit your ground costs, to suit your local costs. And then if you want to change the symbol annotated here, we can go to setup, location setup, and you can change whatever you'd like for the symbol. Next question is a question about the horizontal optimizer. So I won't show that today, just because it does take quite a while to run. Let's come in here, and I'll at least show how it behaves. That's kind of not super interesting. Do I have a? Yeah, let's use this one for an example. And yeah, oddly enough, this is an example that I've used the horizontal optimizer on in the past, and it's actually been optimized. But the optimizer works by, we'll click this, and then we can set this up. So let's tell it that I want to allow all of our IPs, other than the start and end of our road, to be adjusted. So how far can they be adjusted? Let's go with 300 meters in either direction. And then we get a box indicating where each one of these IPs can be moved. And when we do our horizontal optimizer, when we do our horizontal optimization, the optimizer is built on top of the vertical optimizer. So it's going to iteratively adjust your IP location. And then each time it makes a change, it's going to run the vertical optimizer and narrow in on the best vertical alignment for that horizontal option. It's going to do this a lot, and it's going to narrow in on where solutions are getting better, and yeah, find a better solution using your current IPs. Yeah, and to actually run that, so we've got it set up here now. We could hit horizontal optimization, and Now it's going to run. Yeah, it's already been optimized. Question about can I use imperial units? Absolutely. So it's just a matter of setting it up when you start your project to work in either metric or imperial. This project is metric, and this one is imperial. So, yeah, and we have different templates for whether you're working imperial and metric as well. And another question about horizontal optimization. I think this will probably be our last one. We're kind of we're running over our time, but the question is, can I set areas I want to avoid? So, i.e., swamps or defined a defined limit. You can. The solution for that currently is we can trim the tin area down. So if we remove your surface area beyond that, the software is going to hit that boundary, and it's either going to go, it'll go into an infinite fill, which becomes really expensive, and then it's going to keep your alignment on the existing surface. You may see some additional improvements to that in future versions. Oh, and yeah, I guess that's a good question that I should have answered in the examples I chose. So this will be the last one. Can I optimize with multiple templates in my design? Absolutely. So the software itself is looking to adjust the location of the elevation of your road, and it's going to look at the templates assigned at the sampled stations. Just like you're doing if you were doing a traditional design, we could hit assign by range, and we could assign a bunch of different templates within the length of our road. So here I've got our default resource low volume road for the first 400 meters. Then I've got a short section with the spill apron, and yeah, so let's just jump into station 400. And yeah, so here we can see we've got a different template with the spill apron applied versus just anywhere else. And you can build your templates to include logic in them. So things like whether you have a ditch or not, it'll know if you're in fill, it's not going to have a ditch. So yeah, they're pretty smart. And I just answered that next question there. So I think with that, we'll call it a day. And thanks everyone for attending our session.
Thanks everyone. See you next time.